Today, I have prepared for you a motor technology comparison, where I would like to show you which advantages and disadvantages each motor technology has and for which application is the most suitable. This time, I would like to speak about the comparison between induction asynchronous motors, synchronous reluctance motors, and permanent magnet motors. One of the key differences between those technologies is that asynchronous motors are mainly in IE4 efficiency class, but the synchronous reluctance motors and permanent magnet motors are going to IE5 ultra efficiency class and even higher to IE6. Even the IE6 is not defined in standard yet. We are saying IE6 means it has 20% less losses compared to IE5 energy efficiency class. What is also very important that the asynchronous motors can be run directly online and also together with the frequency converter. But the synchronous reluctance motors and permanent magnet motors cannot be run directly online, they can be run only with the frequency converters. Let's talk first about advantages of those three motor technologies. We are using asynchronous motors for decades. We know they are robust and reliable, they have no brushes, they are almost maintenance-free, and what is more important, they can be connected direct online. They can be also used together with the frequency converter wherever it's needed. And as you can see in the rotor, there's a classic squirrel cage where the induced current produces additional heat, which caused that the asynchronous motors has a lower efficiency class compared to other two technologies. The synchronous reluctance motor has no magnets in rotor. The greatest advantage is the one-to-one interchangeability with old asynchronous motors in, for example, IE2 or IE3 efficiency class. It has low power factor, which is one of the drawbacks, but it has really easy maintenance and they are reliable with simple rotor construction. As you can see, on the rotor plate, there's always 4-pole design. There are no magnets inside, there are no squirrel cage, therefore there are no induced current in the rotor. That means this motor is the coldest one among all those three technologies. Last but not least are the permanent magnet motors. We have permanent magnets inside of the rotor to help the developing of the torque in the complete speed range and especially in the low speeds. The high power density and the potential to reducing the frame size up to 3 shaft heights is very important in many machine builders. We have very high power factor, close to 1, and this enables to use permanent magnet motors in one-to-one power matching with the drive and reducing the overall cost of the system. Whenever the application needs that, you can also use this motor without encoder to precise controlling the application. But to better understand in which application excels which motor technology, you also need to know their drawbacks. So let's have a look on disadvantages. Asynchronous motors are, due to their rotor construction, only up to IE4 efficiency class. It's somehow difficult to have a decent speed accuracy without sensor or encoder. We also have a lower efficiency at partial loads, which can be a drawback important for some applications. Additional heat in the motor and bearings are due to higher rotor losses. When we move to asynchronous reluctance motors, we know that the major disadvantage is a very poor power factor. And if you compare among the other technologies, this is the lowest value. Due to that, you need a higher nominal current, and this allows you not to have one-to-one power matching with the drive. So you always have to pick 1 or 2 sizes bigger of the frequency converter, which also rise the overall system cost. The lower torque density compared to permanent magnet motor can be one of the decisive factors from the customer point of view to go to the permanent magnet motor. In permanent magnet motors, we are using rare air magnets. But those strong magnets help us to develop higher torque and also bring many features of the permanent magnet motors. There are also some service and maintenance rules to be obeyed, especially during the maintenance period when you have to put out the incoming voltage and also fix the shaft from rotating, because the rotating magnets can bring a dangerous voltage at the terminal box. There are also high voltage feeding back to the drive when the magnets are rotating. But this is also part of the safety concept we are having in safety instruction of the PM motors. If you are ready to choose the highest energy efficiency motor technologies, you are halfway there. So let's sum it up. We have permanent magnet motors and synchronous reluctance motors. Both are IE5 efficiency class. But from the electrical point of view, electrically perfect are the permanent magnet motors, where you can use the same drive, which means you have the same or lower nominal current compared to asynchronous motor technology. You can downsize the motor up to 3 shaft heights. You have a precise speed control, and also you have 200% overloadability capability and up to 150% overspeed capability. If we have a look on the synchronous reluctance motors, there's the advantage of mechanical compatibility and one-to-one interchangeability with asynchronous motors. They are magnets-free, they are very reliable, easy maintenance, and they have really low intrinsic moment of inertia, so it's perfect fit for high dynamic application. Here we have the top 12 features of the permanent magnet motors. And I would like to show you the comparison of those 3 motor technologies using some of them, and to show you how permanent magnet motor can be a real game changer. Here I have prepared one example. It is a 160 kilowatt motor, 4-pole speed, which means 1500 RPM. As I already mentioned, permanent magnet motor is always smaller in comparison of a standard asynchronous motor and also the synchronous reluctance motor. Here is the example that the standard motors in this power are shaft height 315. Permanent magnet motor is 1 frame size smaller. The other aspect I already mentioned, and here you see the comparison of the power factor. So let's start of the asynchronous motor. It's 0.85, which is quite good on the IE4 asynchronous motor design. But if you choose the permanent magnet motor, you can see the very high power factor, 0.93, allows us to reduce the nominal current. That means we can use the same drive, we can use the same shielded cables between motor and drive, also the incoming cables, and we do not need to change any circuit breakers or protective devices along the drivetrain. But if you choose the synchronous reluctance technology, the poor power factor, which we mentioned as a clear disadvantage of this technology, rise the nominal current, and that means you have to change all the electrical devices which are current related. Drive, cables, and also the protective devices. Synchronous reluctance motors have clear advantage in one-to-one interchangeability from the mechanical point of view. So you can have the synchronous reluctance motor in the same frame size as asynchronous motor. So you do not need to change anything in feeds or stand. What is also very important is the weight comparison. If you have a look on the asynchronous motor in IE4, it's 1,200 kilograms of weight. If you go to a synchronous reluctance motor, it's 965 kilograms, which is very good. But if you have a look on the permanent magnet motor, it's 684 kilograms, which means 43% less compared to asynchronous motor in the same power. Here I have also one example. This is the extreme one. We have 3 shaft heights lower motor in the same power. This is 5.5 kilowatt. And the asynchronous motor is in shaft height 132. This motor in 5.5 kilowatt has 43 kilograms. The small shaft height 90 permanent magnet motor has only 14 kilograms. This is almost 2/3 of weight reduction. And as we already talked about efficiency as the main driver today, you can compare the values down there, and the permanent magnet motor also excels in this aspect. To have the comparison complete, I would like to also show some differences on the rating plate of the permanent magnet motor compared to a standard asynchronous motor rating plate. As you can see on the left side, we have an optimized winding for 380 volts because of the voltage drop at the converter side. We have 2 rotor designs. We have 6-pole design for small shaft heights, which are manufactured in Mohelnice, and 8-pole design for the high frame sizes, which is manufactured in Framstadt. We are using always drive, therefore the frequency on the rating plate is always related to a nominal speed and nominal operating point. The efficiency value, which is stamped on the rating plate of the permanent magnet motor, is the bordering value of the IE5 efficiency class according to a standard. We have also there 2 values, LD, LQ, which are representing or defining the motor behavior at the frequency converter operation. The last but not least is the back EMF value. This value represents the voltage fed back to the VSD, which means to the frequency converter, in nominal point in case of the motor free spinning. This value is always smaller compared to maximum DC voltage at the intermediate circuit and the frequency converter. Looks like now you are ready to make a permanent impact. Go for sustainability and save some energy. Take advantage of our ultra-premium efficient motor portfolio. Achieve higher torques with a smaller frame size, or just boost all the application performance permanently.